Hello everyone! Hi! I'd like to start off by giving y'all a great big wave. That's what that is. And that's a corny joke to start with to hopefully endear you to me a bit and endear you to this project. But anyways, hello, I'm Amin. This is my project. Today we're going to be talking about college admissions data. So our data set is one I got off Kaggle.com. It's a data set about admissions data for minority students. I got it on Kaggle. I'm sure a lot of other students in this class are familiar with Kaggle. You might be as well, my peer reviewer. But I got it off Kaggle. Overview of the data. It's about 400 observations. Now, I wasn't too happy about that because that is a fairly small data frame, and I do like big data. But what I was happy about was this university prestige, and I'll get to that in a second. But the data, it has categories on race, gender, academic qualities such as the GRE and GPA, as you can see there, and university prestige. So university prestige is described in this categorical column, and it goes 1 through 4. 1 is the highest prestige, 4 is the lowest prestige. Universities such as Harvard and Northeastern would definitely be in 1, and you can imagine 2, 3, and 4, and so on. Race is a bit of an interesting variable in this case because 1 is black, 2 is Asian, but 3 is Hispanic, which isn't a race, is an ethnicity. But I suppose in the world of discrimination and racism, those kind of nuances are lost. The gender, we have a dummy for gender being male or not. SES is socioeconomic status. And 1 is the highest, so the wealthiest and most well off, and 3 is the least well off students. GPA is GPA, grade point average, and GRE is the standardized testing. So let's talk about what the business problem is that we hope to tackle. And we can actually identify 3 business problems, 2 for universities and 1 for students. And you can see them over here on the left. So the 2 that we could tackle for universities is the first one is we can help universities understand who are the students that we accept, right? For our prestige of university, what do they look like? What backgrounds do they come from? What are their grades like? Um, for another question for universities is, are our standards fair? Now, our data set is only looking at minority students, which I was a little unhappy about, but it gives us a sense for if we're treating all minority students equally or not. And the last point for students is I'm a student. I want to know what is the important factors for me to get admitted into certain types of universities. So we're also going to take a look at that later. Okay, so let's take a look at our data exploration real quick. One thing we'll note about the data straight away is that it is so clean. I mean, I don't even need this guy with the squeegee or this guy with the Clorox bottle. We don't even need them because this data set is already so clean. There's no missing values. There's no outliers. You can look at this box plot of the GRE column, which is one of our continuous variables. Our other continuous variable, GPA, you'll notice no outliers. And if we look at our correlation panel, you'll notice no strong correlations, no weird distributions. These are our 2 continuous variables again, and oh my god, look how smooth those things are. I mean, geez, beautiful. GPA is a bit wonky, but we'll do, we'll take it. We'll take it. A bunch of, oh no, we have too many smart kids. It's a good thing. Um, Now, because this data is so clean, that means 2 things. One, we didn't really need to transform any variables. We will normally z-score normalize GRE and GPA just because, for example, KNN requires us to do that. But we don't really need to normalize anything. The rest of these are categorical, so we'll just dumbify them. But because our data set is so clean, that means we'll artificially have to dirty it, and that makes these kids very sad. Look at you, professor. You made these kids so sad. Now, there's good and bad news here. Bad news for these kids, it's a nice data frame that we have to ruin. A little bit of fun for me because now we get to have fun in deleting and randomly imputing variables back into our data frame. So over here, as you can see on the left as I'm kind of scrolling, this is the first inception of deleting variables. And so what we do is we go column by column. We randomly delete 25% of the data frame, 5% of the values in the column, and we replace them with NA values. Later on, I developed this random imputation function that'll go through every column in our data frame, find the missing values. If the column is categorical, or if it's, if it's a factor, or if it's numeric, it'll treat it differently. And it'll randomly impute variables for us based on the sample of the column that it's in. Now, let's talk about the types of models that we decided to do. Now, if you're the professor and you're watching this, then you probably see something that's off that we'll get to in a second. But we decided to go, I decided to go with a naive Bayes model, a KNN model, decision trees, and I did on my discussion post that I would actually do a fourth one. And that one really wrecked the house. And that was k-means clustering. Now, I initially wrote that I would do this. When this showed how badly it would fail, or it did fail, I decided to switch over to the KNN model, but we'll talk about k-means clustering and why that failed so badly in a bit. But let's talk about why we chose at least what we did. So we chose naive Bayes, KNN, and distribution trees. Naive Bayes, great at dealing with data frames with lots of noise. And when we have a small data frame like this, especially where we're imputing data, there can be a lot of noise, and there's no real risk of overfitting. On a small data frame, we might wind up in situations where we have to reuse the same data more times than I'd like, or whatever. No risk of overfitting with naive Bayes. KNN. We have a low number of variables. KNN does very well with a low number of variables, and we have a total lack of outliers, which is a good thing to have for KNN as well. And decision trees were really key model for this project, because a lot of this project isn't understanding if a certain student will be accepted, but why they're being accepted. And this is the one that gives us actual feedback on important variables. And decision trees are anyways great at predicting categorical variables. So let's take a quick look at our decision tree. And you'll notice that right away, the first thing the decision tree wants to look at is whether or not the university is rank 1 most prestigious. And then in every case, the second thing it wants to look at is your GPA. This is the decision tree for the full data frame, and if we look at the decision tree for the imputed data frame, we'd see a very similar thing. That was the decision tree for the imputed data frame. For the full data frame, we see a much simpler tree. Are they rank 1, and is their GPA over a certain threshold? And that's the only questions it asks. Now, our imputed data frame asks a lot more questions. You can say this is because of noise, but in other previous trials, with different splits of my data frame, I've seen it go both ways. So I believe this is really just due to random chance. But no matter if they include other variables or not, really what is clear is that the most important variables are rank and GPA. And in other models I've even seen, like over here, GRE come in next, but usually it's just rank 1 and GPA. So I said that I would mention, I mentioned earlier that k-means clustering, and let's talk about it. Let's talk a little bit about failure, not just because this is a requirement of the presentation outline. So here we have our k-means clustering algorithm. I used this function, which is from a library. This function actually, you supply it with a method. You can choose average silhouette width, which is what I chose because it yielded the best result, which is still a terrible result. You can use also total within sum of squares. It has a number of methods that you can decide on. I chose the k-max as 30. And I ran it, and these are our results. Now, what do our results tell us is that the clusters, it decided that the optimal number of clusters was 2. And that the thing that separates them is the GRE and GPA scores, high in each or low in each. And everything else is fairly even. Now, this is some good and some bad news here. The great news is that it means when it comes to universities treating minority and disadvantaged students, they seem pretty even. You can see we have an equal number of Black and Asian students in both groups. We also have an equal number of Hispanic students, an equal number of high and medium and low socioeconomic students, an equal percentages of the prestige. And the only thing that really defines these clusters are GRE and GPA. Even if we looked at different Ks manually, and I have, the only thing that really changes, again, is GRE and GPA. So, even though this cluster is kind of bad for, or this clustering is kind of bad for determining admittance, because, I guess essentially it only really needs 2 variables and it doesn't really need to look at the whole student, but it was pretty bad at determining students. It's really great at telling us that in at least these 400 data points, universities were pretty fair in treating these students. And so that's some data that suggests that, there might not be that much bias in college admissions, although there's probably a lot more robust research that proves me wrong. These small 400 data points, I hope, give you a little bit of hope. Okay, now that I gave my function a little bit of a head start, let's talk about evaluation. Whoa, look at all these tests. Oh my god. Okay, that was kind of a lame joke, but that PowerPoint animation, you have to admit, primo. Okay, so I gave our code here a little bit of a head start to show you some running code I wanted to, and now this part should be ready to run. Okay, awesome. So we evaluated all of them using holdout method and cross validation. I can the way I did my cross validation is by chopping up my data frame into 5 chunks, using 4 of them for training, 1 of them for testing, and retraining the model each time. So what you can see here, the first 2 numbers are through the holdout method, the accuracy of the full and then the imputed data frame, and then through cross-validation, the average accuracy of the full data frame imputations, or full data frame cross-validation and the imputed cross-validation. Now, one thing that's interesting is that you see all this variance in decision tree. That's something we expect. Decision trees are very prone to noise in data, and that's exactly what cross-validation and the holdout method kind of do. But you can see that KNN and naive Bayes are really not that sensitive to changes in data. I mean, particularly naive Bayes, that is rock steady. We evaluated everything based on accuracy just because that's the one metric that everything can kind of agree upon, and especially when you're doing classification problems, you don't really have a mean squared error or an R squared or anything like that. Okay, finally, let's talk about the creme de la creme, the crux of this project, the ensemble. That is very anticlimactic. Let's try better. There you go. Wow, look at that. Ensemble. Okay, so when we take a look at our ensemble, we'll talk about how they perform, but first let's talk about how I made them. So I wound up splitting our imputed and our full data frame into 4 chunks. Now, one thing we wanted to do with this ensemble is we wanted to bag homogeneous learners, right? And part of bagging is making sure that each homogeneous learner has a different data frame. I didn't go the route of giving them each entirely new data frames. I could have done that. I had an idea, but I really wanted to maximize the amount of training data that I gave each one. So what I decided instead was to split my data frame into 4 chunks, or both of my data frames. Don't forget, I have a full data frame and a randomly imputed data frame. So I decided to split them into 4 chunks, and each chunk was used for 2 of the 3 models. So they don't all share the same chunks, and the last chunk was reserved for testing. I wanted to do this because I wanted to maximize the amount of training data I gave them while minimizing the amount of data that they share. But unfortunately, I don't really think that made a difference. Here are the actual functions of how the ensemble works. We train entirely new um, uh, classifiers based on the ensemble data, and because there's an odd number of models in each ensemble, we don't need a voting method. We can just do a strict majority vote because there will always be, there will never be a tie. I decided to use the mean to find that because we're doing a Boolean classification, right? Admittance is 1 or 0. So if the mean is greater than half, that means that 2 out of 3 agreed. 2 out of 3 decided to admit the student, and if it's less than half, then 2 out of 3 decided not to admit the student. And ultimately, these are the accuracies of our 2 models. The full imputation had an accuracy of 0.7, and the imputed model had an accuracy of 0.68. And now you might get the idea that that's kind of odd because that seems pretty much the same as everything else, and you'd be right. So here is all of our different models and all their accuracies, and highlighted in red is our full and our imputed model, and as you can see, they do below average. Now, I think that tells us a couple of things. First of all, I think it tells us that even our individual models are really good at predicting the data because they're doing just as well as the ensemble models, if not better. But I think the other thing it tells us is that all of these models are able to explain the same proportion of data. That 70% of data, it's no problem for them. They don't need extra information. They got it off the bat. But that other 30%, something is missing. Now, it could be a couple of things. We, talk about this here quickly in the summary and key lessons. It's the second point. It could just be that college admissions are somewhat random, and they are, right? That 30% could just be randomness. It could just be that uh, one student had somebody fighting for them in the admissions office and the other one didn't. And that's why one got accepted, one didn't. And it could be any number of reasons. It could just be random. It could be that we need more data, and that's probably likely as well. Maybe we need something about what they discuss in their essays. When did they apply? Early admissions, early decision, stuff like that. Um, and maybe we need some other non-academic information. But again, it could also just be random. One another key takeaway I'd like to take from this project is get bigger data sets. I think it'd have been more fun to do huge data sets, to do huge crunching, to be really confident that your results are accurate, to not have to be worried about the small size of the data frame causing issues and stuff. But the small nugget of hope that maybe you can walk with from this, and it's very small, it's very, very small, is that, hey, maybe there's a little bit more fairness in the admissions process, at least in treating minority students against other minority students. Obviously, I don't have data against white students, but that would also be another key project to do next. Anyways, thank you very much for watching this project. Professor, I assume, maybe a couple TAs, and peer reviewer. And I look forward to looking at your project as well. Thank you.